how to do it. It's called, and here it is right away in your face. It's called the one-sample t-test, what I've done, actually. It's related to the t-distribution. If you Google the t, you will find that it's called the student's t, so you can feel as if it's yours. There is a story behind that, actually, so you can go read about that. It was invented by a guy at the Guinness breweries, actually, back in the beginning of the former century. So it's only like roughly 100 years old or something like that. Anyway, how to actually find this p-value that I just stated to you. What we do is something that looks quite similar to what we did last time. However, still a bit different. Why don't we put some colors to this one? We compute the difference between the data and the null. That's basically the general approach for doing a hypothesis test. Here is a null claim. Here is my data. I compute the difference. And if it's done in an intelligent way, we are ready to evaluate this difference by a probability afterwards. Here is how it's done. Can you see? This is a formula that we can use in a given context. Because for us, the mu0 would be 0, actually. This is a general notation, so we could hypothesize other values, actually. Now we hypothesize is 0 for the difference between A and B. And we basically plug in the mean and the standard deviation and the n, all numbers that we have, so we can find, we call it the observed t-statistic. It's the relative difference between the data, right? Data and the null hypothesis. Relative to the standard deviation of the sampling distribution of the mean that we talked about last time, right? The mean changes from time to time like sigma over root n. So I see the difference between data and null relative to the standard deviation, and sometimes you could call it that I measure it in the unit of standard deviation. That could be a way to say it, actually. So I count how many standard deviations am I away from the null. Having seen, so I compute this number, basically. That's a number in my application. Then I use the right t-distribution and find the p-value like this. So I go in, I have t-ups here, I have minus t-ups here, or the other way around. Anyway, I have it like that, and I compute the p-value as the sum of these two tails. So I define the p-value like that. And then I use the p-value to make my decision. The p-value is a probability. This is where we are using our probability knowledge then to put our evaluation of the data into a probability. Realizing that there is no blacks or whites here. It's not a yes-no thing. Well, at the end of the day, we have to make the yes-no decision. But it's still based on a quantitative information, right? And that is what makes us intelligent about it, that we realize that. More generally about the p-value, because now we see it here explicitly for the first time, given to you as an explicit procedure that you can use now for evaluating the mean when we do a hypothesis test of the mean of something, as I've just shown you. You can sit down and use this. Calculate the t-ops, use the t-distribution as you already started practicing last time. Now it comes again and again. These are the two major tools that I teach you in this course and that I used for all sorts of stats and decision making around on the globe. the confidence interval and the hypothesis test, doing decisions based on the p-value. If you start Googling, you will see some fights over the last decades and all about how much emphasis should be put on one and the other. But that's a subtlety. Both of them have their roles, but they should be used in an intelligent way also, of course. And that's another story. The thing is, it's good to be able to handle both. That gives you a good, those two tools, and you can get pretty far here. Here is the more general definition of the p-value that we have, in a way, applied once now, and that we can use again and again in other contexts. Let's think here. Let's read and let's think. It gives me the probability of my data, assuming the null is true. Let me give you another example that I think you can follow if this was too abstract. What if we go, we'll get back to this example later on in a later lecture. What if we're back at the binomial, at the coin tossing case, right? What if your uncle makes the trick with you and he has this coin and he beats you all the time, or maybe he has 2 coins and he can shift them without you seeing it. And you play the game with him, and then after 20 throws, he had it correct 19 times. How would you evaluate that? How would you test? Now you start getting suspicious, right? You're getting suspicious. I think you have a coin which is not symmetric. You say tails all the time and you win. You win 19 out of 20. We threw this coin 20 times. 19 out of 20 it came up tails. Let's say that's the story. How would you think in making your decision about what's going on here? Wouldn't you think like this? Let me introduce how I would expect you to think. Wouldn't you think like this? If a coin was supposed to be okay, I would expect 50-50 outcome when I throw the coin, right? That's my expectation. I know I'm not going to get exactly 50-50. That's that intelligence I brought with me from the 4th grade or something, of course. But I think I would say, hey, seeing 19 out of 20, if the coin should be 50-50, assuming the null, right? Assuming the null of 50-50 in this case, then 19 out of 20, that's goddamn unlikely, right? So I would compute my own p-value. That's a p-value, at least almost a p-value, right? So in a way, I would claim that most of us have thought p-values many times in our lives. Those of us who thought about things like that, at least, would have thought p-values. Because it is, even though we have to get used to it, and sometimes we make things upside down, and it's easy to get confused about whether we should stand here and look there, or stand there and look back, or what the heck we are doing. But I think it's quite natural, actually, if you think about it. The thing is, we have to be slightly more intelligent. It's not enough just to say 19 out of 20 is unlikely, right? Because what if I took the newborn babies that I mentioned also a few weeks ago? I was considering 35,000 births in Denmark. Would it be unlikely to see 7,501 out of 35,000 being males, for instance? What's that probability? What's the probability to see? What do you think it is? Is it unlikely to see 17,501 out of 35,000 if the single probability is 0.5? Yes, that's pretty unlikely. Right? It happens in less than 1%, only in 0.5% cases. So only in 1 out of 200 years, we would see 7,501 males being born out of 35,000 births. Should we use that as a conclusion to claim that the underlying probability of males is not 50-50? No. We should be slightly more intelligent. Going back to the 19 out of 20, the way we should think is, what is the odd event? What is the probability that should become our p-value in this case? Well, it's both 19 and 20. We should include in our evaluation of how odd is 19, right? How unlikely or likely is 19? Well, we should find the probability of the event 19 and 20, but then actually 0 and 1 is just as unlikely as the 19, right? So the p-value should not only be 19, it should be 1920, and it should be 0, 1, the two tails. That's what I did for the t-statistic. I computed I take both the tails, right? And now we get the example in a second, so let us move forward to the example. The way we use the p-value, though, is given in this table. There is an important split in the table. Could have made it more clear. Globally, the 5% level, we've seen that already last time. Globally, the 5% level is being used as the distinction between when we have proved something, found something, and when we have not. And if we want to be slightly more intelligent about it, the smaller the p-value, the more strong evidence against the null we have, right? If the p-value is not below 5%, we have proved basically nothing. So, when we read in the news from Berlingske, business news about Novo Nordisk, that they have shown that this drug has this effect compared to the other drug, and they know for that for sure, or they have documented it, proved it, it means that there was a p-value becoming lower than 5% for them in that study. That's what the conclusion is based on. Let's do it. I compute the test statistic for my sleeping medicine example. I plug in our case, we test the null hypothesis of the mean being null, 0. I plug it in, and I get a standardized t-observed statistic of 4.67. Already here we will start learning, this is a large difference, right? A t is something which lives basically on plus minus 2, a little bit depending on the degrees of freedom, on the n. So 4 seems to be a pretty large difference between the null and the data. And here we go. We compute the p-value as it was defined to us in the method box by plugging in the observed 4.67. And then we also take, that's the 2, and I use the symmetry. So I get both of the tails in computing the p-value. And I use my inbuilt pt function for doing it. And I get my p-value of around 1 out of a mil. So if I use that value, I take that value, I go back to my table 3, and I look in table 3 how to use that probability. Table 3 tells me I'm here. First of all, I'm below the 5%, but secondly, I'm so much below, so I would say that I have a strong evidence against. This table here is putting in slightly more intelligence about interpreting the p-value that is being typically probably allowed by the FDA and other certifying agencies. Probably certifying agencies, they have to obey to the rule, at the end of the day at least, yes or no. So they have to put a limit. If it's below, and that's typically 5%, we say yes. If it's not, we say no. Right? So that is there is an agreed limit question.
Yes, in your formula where it says 2 times 1 minus pt, where do you get, no, little further ahead.
Down this way?
Stop. Where do you get the 9 from?
Good question. Where do I get the 9 from?
Is it just n minus 1?
It's n minus 1, exactly. And it is stated here in my... No, so this is to use the right t-distribution, which is by definition or by theory, you should say n minus 1. Another question? Is n always 9? No, it's only 9 because, no, n was 10, giving the 9, n minus 1, 9 here, right? N could, of course, be anything. Tomorrow you make an experiment with 54 people, so the degrees of freedom would be 53 in that case, right? Yeah. Here are the manual stuff in R. This is just showing the formula we've just used, how you could plug it in manually in R. Let me not dwell on that, but let me show you that the t-test function that you met last time already gives us the result here. It computes the t-ups. It tells us what the degrees of freedom is. I just plug in the data, right? I don't do anything else. I have the list of data and I plug it into the function. And if I don't say anything else, it does these things for me, right? So it's a bit more general, abstract about all this hypothesis testing and this significance word that we will be using and people are using a lot. We do hypothesis testing when we make decisions, right? I've motivated that already. Here is the terminology, the wording that we use around it. We say that we reject a null hypothesis. That's what I just did. I rejected the null. I falsified, I use that also, but the general term used most often by people would be that we have rejected, afvist in Danish, rejected the null, and we do that when the p-value becomes small, right? What is small? Well, that is to be decided by both parties in a way. If you are two parties, you can, of course, agree on the risk level, because this is a kind of risk level. We will learn that more in later. Usually that risk level is agreed to be 5%. That's the most commonly used risk level for these activities. But it could be different. There could be cases where we want to use a different risk level. And that is called the significance level. This alpha, pre-specified or agreed or given by the authorities, there is an alpha, we obey to that. If not, we use this dangerous word that we have to use with care. If we do not reject, it's less dangerous to just say we do not reject. So we either reject or we don't reject. But I have to share with you that there are many people out there, and we are also chosen to use that word, although it's a bit dangerous. When we don't reject, we often say that we accept. The dangerous thing here is we should be careful not to interfere, accept with prove. Because just because we accept, we cannot prove that a new drug is better than the old one. It's not the same as we have proved that they are the same. That's a quite different thing. So it's just our inability to prove something when we accept something. So we'll get back to that. And we say that something, like we've just tried with the effect of B relative to A, we say that an effect is statistically significant if the p-value is small. Right? So that's the way we talk about it. This is when something goes in the paper, blah, 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 they found something that means that it became significant in the statistical meaning. This word significant has also of course, a regular verbal English language meaning, which is related to it. So, to use those words once again, if we use the sort of globally chosen 5% level, we would, in the sleeping medicine example, conclude that we reject the null because the computed p-value was below the 5% level, right? So we conclude that we reject the null, I already did that, and we could phrase it the way that we have found a significant effect of medicine of medicine B compared to A, right? And since we can see that B is better than A, that is our conclusion then. In a way, we just prove they're different, but by looking at the numbers, we are allowed to conclude that B is better than A, actually. Otherwise, it would be silly. So, we jump